All right, well, here we go again. We are now looking at the 2015 free response question number 1 on the BC test. It is in a topic that I like to call interpreting rates of change. This particular question, and the ones in this series, there'll be 4 questions from 15, 16, 18, and 19, are calculator required questions. So we'll be using the calculators to figure them out. However, this year's 2020 AP test online does not require the use of a calculator, so I anticipate that the questions could still be similar. However, there might be some more simplistic equations or perhaps tables instead of equations, and we'll go over some of those later on as well. But this is the 2015 question just to get you started, and we'll see how it goes. So the scenario is that you have a rate. You have a rate of water flowing into a drain pipe modeled by this equation. And you have the rate of the water draining from the pipe, which is given by this equation. And we're making an assumption there are already 30 cubic feet of water in the pipe. So here we go. Question number 1. How many cubic feet flow into the pipe during the 8-hour time interval? Well, the amount of the water flowing in is just going to be the integral of the rate. So the amount of water is going to be the answer to this question. And then your R is here. So all you really have to do is plug it in and find out the answer. So again, if you had a calculator, it'd be a pretty straightforward one. Without a calculator, I wouldn't even bother. So if you can do this setup, then you know how to do the problem. But when you calculate it, and you calculate just 3 decimal places, you get the fact that there are 76.570 cubic feet of water being plumped into or entering the drain pipe. Okay? Now this 30 is irrelevant right now. It means it started with 30. In the 8 hours, 76 got added in, but there's also some that got taken out. So right now we're only wondering how much went in. And there it is, 76.570. Now, is the amount of water in the pipe increasing or decreasing at 3 hours? All right. So we know the rate entering. If I calculate the rate at 3, which I've already calculated over here, if you plug that into your calculator, the rate of 3 is this. So what is this telling you? Cubic feet per hour. So at that moment at 3 hours, the amount of water entering the pipe is changing at a rate of 5.086 cubic feet per hour. Now the D equation is how much would be leaving the pipe. So at 3, and again, here's your equation for D, and I just put it in a calculator because we're using these 2 equations here. So the amount of D for draining from the pipe, if I put in 3, I get 5.4 cubic feet per hour. Remember, these are the rates of change. So the rate of water entering is less than the rate of water that is leaving. So I know, since this is true, if more water is leaving the pipe, then the amount of water in the pipe is decreasing. And there are many ways to justify this answer. I generally have a justification right here. But I'll put it more specifically. The water is decreasing because the rate draining, I didn't even spell that right. And I erased too much. Okay, the amount draining is greater than the amount entering. Okay? So if you look at the scenario, what's going on? It's something that's always in motion. Something is entering, something is leaving. Now it's leaving at different rates. And it's not a constant rate, so the rates are actually going to be changing. So you can't make generalizations just yet. But there's your B answer. When time is 3 hours, water is leaving the pipe faster, so it is decreasing. All right. So at what time is the amount of pipe in the water a minimum? So how do we figure out the amount of water? Well, again, the amount of water is given by 0 to a certain time. Okay. We don't necessarily know the time. Okay, because the time is what we're looking for. So this is R of t, and I probably should have used a different variable for the water entering. You know, we'll just leave it for now. It's okay. Whoops. But I don't want to use that pen. Okay, minus, that's the water entering, minus the water leaving. Whoops, which is not R, it is D. Now we also know there's 30 in the pipe to start with. So that's a general expression for the amount of water in the pipe at any time. So if I want to know when it's a minimum, why take the derivative? Well, the derivative of an integral, according to the fundamental theorem of calculus, is just the function. That's probably why I should have had a different variable there. You're not supposed to put t into t, but that's okay. And the derivative of this is dt, or d of t, and the derivative of 30, of course, is 0. So second thing, I want to find a minimum. I want to set the derivative equal to 0. So really, what am I looking for? I'm looking for when does the rate of entering equal the rate of exiting. Kind of makes sense, does it? There's going to be a spot, a critical number, where these two values are the same. So beforehand, it might be rising, it might be lowering. I'm not sure. I haven't looked at the graph. So let's say it's lowering, and then it's going to hit that point where they're the same, and then it's going to flip positions, possibly. So what you do is you put it on your calculator and you graph it. And I found out that the intersection point was at 3.272 hours. Now there's two things you can do at this point. You can show that this is a minimum, which again you can look on your calculator. You'll find that the amount of leaving is actually higher at this moment. Because remember what we said, we calculated from this before. At 3, we know it's draining faster. So anything less than 3.2, water is leaving. And anything past this, water is entering. Which means this is a minimum. So no matter what your graph looks like, the amount of water it was leaving, and then it bottoms out at 3.2, and then it increases. So that's your minimum point right there. So by showing that you have a minimum point, I mean, that's what you have to do now. Let's just write it out. So a good explanation is, okay, the water is a minimum. At the time t equals 3.272 hours. All right. Because, now again, you can't accept the chart as the answer, so you got to be very clear. So you can say that the draining was faster than the entering, all right, before 3.272. It was down just a smidge. And it was less than the entering after 3.272. And that's one way to justify it. The other way to justify it, and you can see that on the actually scoring rubric, is because they're asking for an absolute minimum, you can just test this point and test the endpoints, test 0 and test 8, and see where the lowest value is. But to me, this is an easier thing to do because if I can show this is the minimum, then it has to be an absolute minimum because it's the only time that those two graphs intersect each other in the interval 0 to 8. All right, and lastly, we're going to set up an equation that answers this question. And the question would be if the pipe can hold 50 centimeters of water before it starts to overflow, write an integral, or write an equation that involves integrals that gives the time w when the pipe will begin to overflow. So we're going to use that w as our variable for time. All right. So we know pipe starts with 30 cubic feet in there. We know it enters at the function of r. We just don't know when. We know it starts at 0 and it goes to a time w. We also know that it leaves at this rate. So I'm going to subtract this rate away. Again, from 0 to w. And what do I want to know? I want to know if this ever hits 50. So that is an equation, if we solve it for w, that will tell us when the pipe would begin to overflow. Now, if you want, you could certainly combine these two and just say r of t minus d of t, and that's the same thing. But I always look for efficiency and speed when I do my answers, so this answer says it all. All right, so that is question number 1 on the 2015 test. It deals with interpreting rates. So this 2016, 2018, 2019 are very similar, and I will post those solutions at another time. So thanks for listening. Have a great day.